Our next speaker today then is Uday Kashalaka from Surmet, speaking to lightweight and thin curved transparent armor for discreetly armored vehicles. Uday?
Yes, well, thank you very much. And thanks all for attending this presentation, and wish you a good afternoon. I'm going to talk about DHS SBIR Phase 2 that is ongoing. And the subject area is armor, transparent armor for discretely armored vehicles. So the need or the potential new capability that is required is in discrete armoring, which is vehicles that look like regular unarmored vehicles, but in fact provide protection to the occupants. And by making such vehicles as close to the production vehicles as possible, it does not attract attention from the enemy, which is the first axiom of survivability. So going with conventional glass armor, the issues are that it is very, very thick for certain required ballistic performance capability. And that thickness makes it more prominent, if you will, exactly opposite of what you want to have the armor be. And that promotes, if you will, detection by the enemy. The state-of-the-art glass armor is also very heavy, and that compromises the vehicle range, performance, maneuverability, stability, and so on. And so the starting technology that our program is based on is Surmet's Alon transparent ceramics. These materials are much, much harder than glass, much stronger than glass, and as a result, compared to glass-based armor, we can provide the same ballistic performance at less than half the weight and thickness. The challenge is to fabricate these very hard transparent ceramic materials into a curved shape that provides the discrete armoring, if you will, for armored vehicles. And that's the subject matter of this SBIR Phase 2 program. So there are organizations that would benefit from that within the Homeland Security, include the Coast Guard, the Customs and Border Protection, Cybersecurity Infrastructure Security Agency, potentially the Secret Service, as well as the local police enforcement, police and law enforcement offices. There's a lot of interest in the Department of Defense, Department of State, and then certainly there are non-government applications in armored limousines and vehicles. So again, the baseline technology, the weaknesses, as I mentioned, very, very heavy and thick, that affects the vehicle performance and also compromises compromises the discreteness, if you will, of the armor vehicle. There are 3 transparent ceramic material candidates that can reduce the weight and thickness compared to glass armor. They are Alon, Sapphire, and Spinel. And the current polishing process for making these components, these materials into curved articles is very expensive. To give you an idea, the extent technology, the cost per window just for fabrication is on the order of $100,000. So we started on a program and technology to bring this cost down from 100,000 to order of magnitude lower, as is needed to make this technology viable. So the customer requirements for this product area, the overall requirements or let's say the desires are that the transparent armor weight and thickness should be less than half compared to that of glass armor. The polishing cost should be no more than 50% greater than flat Alon armor. The field durability compared to the glass armor should be an order of magnitude better, and also low light situational awareness, which is when the occupants in the vehicle wear the night vision goggles, how much light or how much situational awareness they have of the outside low light area. That situational awareness we want to be 50% higher than glass-based armor. So these are some of the metrics that we had set up. So this here shows the various steps in manufacture of curved transparent ceramic components. I'm not going to go into the details, except to say that we have focused on innovations that will greatly reduce the cost for each of these steps. And certainly people who are interested, I can have a deep dive to discuss some of these innovations and the resulting achievements. So the first step in that is to make a blank to near-net shape, and our innovative technology, we call it hot forming, that has shown that we can make the parts to net curvature and the net thickness. And then after that, we go into the fabrication steps. The first one is called generation, in which we have shown here that the generation time compared to the existing technology, we reduced it by 1/5. So basically, increased the material removal rate by 500%, and actually end point of at the end of this step, we are much closer to the final component compared to the existing technology. And then the next step, the lapping and polishing step. Similarly, we have demonstrated that the roughness and the thickness control and the curvature control requirements were met through our technology. And these here again show the metrics as to how much we reduce the lapping time by, as well as the polishing time. So you can see all of these achievements were close to an order of magnitude reduction compared to the extant technology. So this here shows, the curved windows. The curvature is slight. So to show the curvature, we are showing the profile over here. So these are the curved windows that you can see with the aid of this reference flat, if you will, that we have in the form of a level, spirit level over here. And so we have made these components to the near net curvature, and then shown the fabrication processes to convert them to polished and transparent parts at a much higher efficiency, lower cost than the extant technology. The goal is for the end goal for the program is to make windows that are roughly 500 by 700 millimeters. That's roughly the size of a typical vehicle window, side windows. And we have designed and built lapping polishing machines capable of windows in this size. And we are in the process at this point of demonstrating the technology at full scale component level. So these are some of the specific performance metrics, if you will, that we had set, and then our achievements. So in terms of weight, we had set a 50% reduction compared to glass armor, and we have shown 50 to 60% reduction for relevant threads. And it has been proven through third-party testing as well as testing at certified labs. Similarly, the thickness also we have shown same type of reduction compared to glass-based armor. The polishing cost, we have shown that it's only about 20 to 30% higher than that of flat Elon armor, but we need to generate more experience and data on full-scale components, and that's what we are working on now, and hoping to continue that with the future work in this area. Field durability is much lower ballistic failures in field compared to glass-based armor. So at this point, again, it looks promising based on lab and limited field testing work that is done. More field experience is needed, and that's what we are hoping to take this technology to for evaluation and verification. And lastly, the night vision goggle transmittance. This is for the low light situational awareness that I mentioned. So Elon armor provides close to 50% increase based on lab results, and again, more field experience is needed. So the current state of development of this technology is that we have Elon heat treatment equipment that is production qualified. We have this equipment in-house in our facility in Buffalo, New York. And then we also have curved polishing equipment that has been proven at this point at the subcomponent level. It is designed and has the size capability to fabricate the full-scale car windows, the 500 millimeter by 700 millimeter size windows. And we are working on demonstrating at the full-scale component level at this point. So a little bit about Surmet. So we were founded in 1982. The first 20 years, our focus was in thin film coatings technologies, and that led to products such as telescope mirrors. We are supplying mirrors for space telescopes. The one that has gone the farthest is the mirror on NASA's Lorry spacecraft, which is now hurtling along the outskirts of our solar system, and the mirror is performing very well. We have also in the past supplied electrostatic chuck components, and that, hard to believe, became the world standard back in the 90s and the early first decade of the 21st century. And that was our legacy products, if you will. And the current business is in Alon and Spinel transparent ceramic windows for a number of applications. The mainstay is in defense systems. We are supplying products to almost every major defense prime, and the products have ranged from helicopters and aircrafts to reconnaissance systems, high-flying planes, observing things that are going on the Earth in areas of interest, if you will. We are supplying spherical domes for missiles and other defense systems, as well as windows for subsea, for space vehicles, and for biomedical and industrial systems. So we have excellent fabrication as manufacturing capabilities, both the heat treatment as well as fabrication of those components into optical precision optics components. This here just shows a comparison with glass armor, the field durability of Alon. So this here shows ballistic performance. These are high-speed shots of a bullet hitting the armor. On the top here, I'm not sure if you can see it very well, but on the top here is the Alon. And what I want to say is that compared to the glass, Alon is less than half the thickness, half the weight. Those numbers are written here. I'm not sure if you can see it, but we can share details later on. And over here, you can see that the bullet is stopped versus in the glass, the shrapnel, you can see the debris from the event, comes through the back face. So this is here the Alon armor window that was tested there. This is the glass window that was tested there. You can see how much thicker the glass window is compared to the Alon window. In spite of that, the glass window could not stop the projectile versus the Alon window stopped the projectile. The reason it works is the high hardness and strength of the Alon material. So here the projectile, after it defeated the glass armor, stayed pretty much intact, and that is why the armor could not stop it. In case of the Alon armor, the core gets decimated into essentially very fine dust-like debris that we had to go with a magnet and collect. And that high hardness and high strength of the Alon leads to this effective breakup of the projectile core, and that leads to the high ballistic performance or the protection that Alon armor provides compared to glass-based armor. Here is a quick graphic of the rock strike performance in vehicles. In the field, there are rocks flying from the vehicle in front of you, and if the windshield gets cracked, obviously, it's not a good situation. So with the Alon armor and the glass armor, we compared the foreign object damage resistance using an engineered projectile, an engineered granite rock, if you will, that was shot with an air gun, and we measured out the speed just before the rock hit the window. So these are comparative, again, high-speed shot, performance of Alon window versus the glass window. And without going into the detail, the Alon window stopped the rock at speeds 3 times that of at which the glass window broke without breakage. Okay, so we went to the highest speed, which was 3 times the speed at which the glass window broke, and the Alon window did not even get scratched at that speed. So these features, if you will, lead to tremendous non-ballistic reduction of non-ballistic failures. And I won't go into the detail over here, but I wanted to say that we are not just a company doing the technology development. We are fully vertically integrated manufacturer of Alon ceramics, and we do the synthesis of the starting powder all the way to the final optical fabrication. Our each fabrication production run consists of a metric ton of load, and we have deployed our product in hundreds of military helicopters and aircraft. And now, with our internal manufacturing capability, we are addressing the vehicle market, and especially the curved armor for discretely armored vehicles. So that's the area that we have identified as a business area to focus on in the future, and look forward to getting any feedback that we can get from this August group, especially information on any potential opportunities, requirements that you are aware of for curved transparent armor or even flat transparent armor, and any candidates, contacts at any candidate customers or end user organizations that you may be aware of. So my contact information is shown below. And again, I appreciate your time and interest. Thank you.